have an x and a y that are the sample space of two random variables, x and y. The Cartesian product of these two sets, okay? Now I denote omega as the sample space of the Cartesian product of x, y. So I have x and I have y, I multiply them, then I have a bunch of ij. These are all the possible ij I can have for this x Cartesian product y. I can define probability. So for example, I have this table. What does it mean? This box means that the probability of x is 1 and y is 1. So this means the probability that x equal 1 and y equal 1 is 0.05. And for example, this box means the probability of x equal 3 at the same time y equal to 2 is 0.3. This saying that I have two events occur at the same time. Random variable x takes the small x value and the random variable y takes the small y value. Here is an example of joint probability of two random variables. Suppose there are a bunch of people. Calligraphic x represent the sample space of about whether or not they are wearing glasses or not wearing glasses. The calligraphic y is the sample space of whether or not they are wearing hat and not wearing hat. The Cartesian product will be wearing glasses, wearing hat, wearing glasses, no hat, no glasses, hat, no glasses, no hat. Okay, so this is a table. What does this 0.45 mean? It means if you randomly pick a person, there is a chance 0.45 that this person wearing glasses and not wearing hat. What does this 0.15 mean? This 0.15 mean if you randomly pick a person, there's a chance that this person wearing hat, not wearing glasses. And notice that what are these? Joint probability is a kind of probability, and therefore the axiom of probability has to hold. And therefore all these three axiom 1, 2, 3, that means probability non-negative, probability of sample space is 1, and the sum rule also holds. With the joint probability, we can talk about something called marginal probability. This simple, the probability of capital X equal to small x. Notice that this symbol have no y. What does it mean? Only looking at x regardless of y. This means for all the y, we take all the possible small y in the sample space of y, and then we compute all the joint probability, and then we take the sum. So for example, what is this? This is the probability of wearing glasses. So we don't care whether or not it's wearing hat or not hat. So this is the same as probability of x equal to g. So that means we are looking at this column is 0.5. So what does it mean? It means it is a probability of x is g, that means wearing glasses, y is h, that means wearing a hat. So plus x is g, h is wearing glasses, y is n, is not wearing hat. So it's saying this number plus this number give us all the probability of wearing glasses. We add these two numbers, it's the same as we don't care about the y dimension. We don't care. We collapse along the y dimension. And then suppose we are considering the probability of not wearing hat. So it means we are looking at this. That means we don't care about wearing glasses or not wearing glasses. So we should sum these two numbers. So this number corresponds to this one. This is x have glasses, y not wearing hat. This 0.35 means x have no glasses, y is wearing hat. So these two numbers add together, 0.45 and 0.35 give us 0.8. This kind of probability that we are given a probability of a table that is a joint probability. If we only care about one of the attribute, we don't care about the other attribute. This has a name. This is called marginal probability. This is a table. So that means for all the x, we have n event. That is x1, x2 up to xn. Okay. And for the y, we have m event. So for the calligraphic y, we have m event. Each boxes correspond to one particular joint probability. So for example, this boxes means the probability of x takes x2 and y takes y2. Then what happens if we augment this table? We augment this table by, if we take all this value and sum all of them, it gives us this. The meaning of this action is that, first of all, look at this expression. This expression has nothing on y. That means we only have one thing in common, that is x is x1. So that means this number means we ignore y, and what's the probability that we only see small x1? And similarly, what is this number? What is this number? It means we only looking at summing all the element here, ignoring all the x, we only care about the y. And the last thing about two random variable is the conditional probability. So we write a bar here. So this simple probability of x equal to x given that y is called a conditional probability. It means we are knowing y is y already. We are knowing. We want to ask the probability of x is x. Okay. So the definition is like this. The probability of x given y is the joint probability of xy divided by the probability of y. So this is the definition. So here's an example. Suppose I have this table. What's the probability of x is 1 given that y is 1? So what does it mean? It is the probability of x1, y1 divided by the probability of y1. So by looking at the table, what's the probability of x1, y1? The probability of x1, y1 is exactly these boxes. So we have this 0.5. What's the probability of y1? The probability of y1 is that we only care about y1. So we sum these three numbers together. We will get the probability of y1. So we add all these three numbers together, it gives us 0.3. Then we take this number, it will give us 0.1667. What does that mean? It means if we know that y is 1, then within these three boxes, this occurs with a chance, this. Another example, what's the probability of x is 1 given that y is 2? So by definition, it will be the joint divided by the marginal. So joint of x1, y2, joint of x1, y2 is this, which is 0.25. Now we want y2. y2 means we're only looking at y2. Then we add these three numbers together, it gives us 0.7. Then we divide these two numbers, then we will get the probability. Can we have probability y equal 0? No. Why? Because we do not allow division by 0. Two random variables are statistically independent if their joint probability can be decomposed into product of their own marginal probability. So that means what? This implies conditional probability is the same as marginal probability. So recall that this is conditional probability. Conditional is defined as joint divided by marginal. So we have this expression. And by definition, we have independence if we can split them. So we have split them into two terms. And then this term cancels out with these two terms, we have this. So what does it mean? It means the probability of x given that we know y is the same as probability of x. It means the information of y tells nothing about x.